Welcome to another video of the EDXL IGCSE data chapter. Okay, in this chapter we are going to talk about number systems and bases, what they are. Okay, the language of computing, what do we mean by decimal, by binary and hexadecimal. So see here, what is a number base? A number base determines how many unique digits a system uses to represent values. We have gotten base 10, which is decimal. In base 10, we have gotten 0 up to 9, which is just 10 unique digits. Okay. And that is just the language of everyday human life. Every day just we count with decimal. Okay. Then we have gotten binary. Okay. Binary, that is just the physical language of computer hardware. And binary has gotten only 0 and 1. It is base 2. So it has gotten two different digits. Okay. Then hexadecimal is base 16. Okay, it has gotten 16 different digits, 0 up to 9, and after that A, B, C, D, E, F. Okay, we can use them as numbers. Okay, then hexadecimal is the bridge language used by programmers. Computers do not work with hexadecimals. Okay, computer cannot understand hexadecimals. It is just used by programmers to make their own lives easier. Okay, we will just explain how. C decimal is base 10, the human language, digits available, that is 0, 1, 2, 3 up to 9, so 10 different unique symbols. And how it works, every column to the left is multiplied by a power of 10. The value of the first place is 10 to the power of 0, which is 1, so the value of that is 1. So 9 here, it means 9. Okay, then 10 to the power of 1, the next one, okay, which is 10. A 3 here means 30. Okay, then the next one, 10 to the power of 2, which is 100. A 6 here, it means 600. And 10 to the power of 3, that is 1000. A 3 here just means 3000. Okay, so that is place value 1, 10, 100, 1000, 10,000, whatever. Okay, and how do we just simply calculate that? See, 3000, so that is 3 multiplied by 1000, so that is 3000, plus 6 multiplied by 100, that is 600, plus 3 multiplied by 10, that is 300, plus 9 multiplied by 1, it means 9 ones we will have, so that is 9. Okay, so as a result we have 3639. So that is daily math that you have been working your whole life with that, so not very difficult. The next one is binary. Binary is base 2, the machine language. The processor works with this. Okay, and when you're storing data, it's just stored like this. So digits available is 0 and 1, only two unique symbols, okay, representing physical transistors, on or off, transmitting electricity or not transmitting electricity. How it works, every column to the left is multiplied by a power of 2. So see, in denary that was power of 10, 10 to the power of 0, 10 to the power of 1, 10 to the power of 2. Here in binary we have gotten 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So place value of each one here is just something like that. 2 to the power of 0 is 1, so place value of the first one is 1. Then place value of the next one is 2. The place value of next one is 4. The place value of next one is 8. Okay, so we will just continue for 8 bits that mostly in IGCSE we work on, that is 2 to the power of 7, which is 128. Okay, so if we have gotten just on and off ones and zeros, the ones we have 1, it means yeah, we have that number. If we have 0, it means we do not have that. Okay, so key concept, digital information processors contain billions of transistors. All data in program instructions are represented purely as streams of millions of ones and zeros. So inside your computer you have just gotten millions of ones and zeros. Okay, you do not have any symbol for A or 4 or just things like that. 4 is changed to binary and stored inside computer, and computer works with that in the binary state. The next one is hexadecimal. Hexadecimal is base 16. This is the programmer's bridge. Okay, it means we do not work with this in daily life, and computers do not understand this. Programmers have created this to just simply make their own lives easier and to work with binary numbers a little bit with more ease. Okay, so we have gotten 16 unique symbols, that is 1 up to 0 up to 9, so 10 symbols here. Then for 10 we just use A, for 11 we use B, for 12 we use C, for 13 we use D, for 14 we use E, and for 15 we use F, capital letters. Okay, now for 16 we will just have 1 0. Okay, it means one set of 16 and zero set of ones. That is just base. So crucial rule: computers never process hexadecimals directly. They only understand binary. Hexadecimal is an artificial bridge created strictly for humans to easily handle large binary numbers. Okay, what do we mean by this? For example, okay, see, if I want to show a color, Alice blue, okay, inside the computer, that color is stored inside computer or just works in processor, something like this. Okay, 1 1 1 1 0 0 0 0 1 1 1 1 0 0 0 1. So see, it is hard to read and hard to memorize, and you may just easily make typing mistakes there. Okay, but see, changing that to hex, that becomes easier. So it is shorter, it is more readable, and you can just copy it more easily, or even while typing. Okay, how does it work? See here. So 1 1 1 1, okay, that will be just kind of 15, and that is the largest number we can store in 4 bits, and 15 is just F, okay, that is the highest digit of hexadecimal. So that is changed to F. So see here, 4 bits or 4 bits F, 4 zeros, that is 0, okay. Then again 4 ones, that will be 1F, 15. Then see here this one, 1 2 4 8, we have gotten only one 8, okay, so that is just 8. Then you have 4 ones and 4 ones, that is just again F and F. Okay, so the golden rule here is 1 hex digit is equal to 4 binary bits or enable. Every 8-bit byte is perfectly represented by exactly 2 hexadecimal digits. See, this is FF, this is F8, and this is F0. Okay, something like that. So look at this matrix. Okay, here we have gotten denary 4-bit binary, and we have gotten the hex notation of that. So 0 is 4 zeros in binary, and that is 0. Okay, 1, so that is binary of that. So we have this. Okay, you can just pause the video to look at this. 7 will be just kind of this. See, 1 plus 2 will be 3, 3 plus 4 will be 7. So this is 7 in binary, and yeah, in hex notation as well, we have gotten 7. Okay, 9 8, so 0 1 0 2 0 4 and 1 8, so that is 8. Okay, and 1 8 and 1 1, that will be 9. So we have just gotten till here. Then after this, see here, 10 in binary, it will be stored like this, and that is A, 11 B, 12 C, okay, 13 D, 14 F, and 15, which is just 1 1 1 1. That is the largest number that we can store in 4-bit binary. That is just F. Okay, and some questions here say convert a 11010111 to hexadecimal. So we will just simply take them 4. Okay, so these 4 first ones, 4 1101, so that will be 1 plus, now 2 we do not have, 4 we have, 1 plus 4 will be 5, and 5 plus 8. Okay, 5 plus 8 will be 13. Yeah, and see, 13 here is D, so we just simply wrote D. And 0 0 1 1 1, okay, 0 1 1 1, where do we have that? We have it here. See, 0 1 1 1, that is 7, so 7. And convert B9 from hexadecimal to binary. So now we have gotten B, so change it to B. So we have gotten B here, yeah, that is 1 0 1 1, so 1 0 1 1. Then we have gotten 9, 9 is 1 0 0 1, so we have gotten 1 0 0 1. So it is very easy to change from hexadecimal to binary and from binary to hexadecimal. Each 4 digit of binary will change to 1 hex digit, and each 1 hex digit will change to 4 digits of binary. Okay, so that makes your life quite easy. Then see, use of hexadecimal in real world. As we told you, programmers use hexadecimals to just make their own lives easier. Okay, it is very difficult to memorize all the zeros and ones. Okay, so they will just make it shorter to hexadecimals, and it is very easy to just convert to back to binary, okay, compared to denary. So that's why it's used. For example, MAC addresses, you might have seen this in your mobile phones or things like that. Okay, So MAC addresses or media access control, that is something like this. Now in computer, this is stored as binary. Okay, so a unique identifier assigned to device network interface hardware identification, and much easier to print on a device sticker than 48 binary bits. This will be 48 binary bits, and think about just when you need to use that. So that will be just quite lengthy, and because it is ones and zeros, you have gotten a high probability of making mistakes. So this makes your life easier. Okay, or for example, to show colors, true colors. Okay, this two first one shows the amount of red, the next one shows amount of green, and the next one shows amount of blue. Okay, so 24-bit color depth used in digital graphics. So 8 bits, it means 2 hex digits for red, green, and blue. So for each one of them, we'll have 8 bits. Change it to binary or change it to hexadecimal, you will have 2 hex digits. Okay, so here see, we have gotten 3 set of 256. So 356 combinations, 256 combinations, 256 combinations. That makes 16.7 million colors. So in that 24-bit color depth, you can show 16.7 different million different colors. Okay, so that is and that is just neatly shown only in 6 digits with the help of hexadecimal. The master key number system, decimal, binary, and hexadecimal. Primary use for decimal, that is humans. For binary, that is computer hardware, and hexadecimal for programmers. Okay, available digits 10 digits 0 up to 9, binary 2 digits 0 and 1, hexadecimal 16 digits 0 up to 9, and A up to F, capital letters. Then multiplier, that is power of 10, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, is starting from 10 to the power of 0. Yeah, multiplier. Okay, powers of 10, the place values 10 to the power of 0, 10 to the power of 1, 10 to the power of 2. In this one, that is 2, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Okay, in hexadecimal, that is power of 16, 16 to the power of 0, 16 to the power of 1, 16 to the power of 2. Okay, so that is this kind of. In place values, first 3. Okay, in here, place value of the first one is 1, then 10, then 100, continue. In binary, that is 1, 2, and 4. In hexadecimal, that is 1, then the place value of the next one is 16, the next one 16 to the power of 2, that is 256. So 256, that is place value of that. Okay, going to the exam practice questions or exam practice. See, identify one reason why programs use hexadecimal notations. These are just questions from past papers. Okay, so it is easier for a computer to understand. So we just said that computers only read binary, they cannot understand hexadecimal. Okay, easier for humans to read, that is correct. Takes up less computer memory, it takes up exact same memory, because in computer it has to be saved in binary. Okay, and quicker than binary to execute. Again, computer just executes only binary. Okay, so it is easier for human to read. The next one, explain the relationship between a byte and a hexadecimal digit. It has gotten 2 marks. Okay, so one hexadecimal digit perfectly represents 4 bits, enable. So that is 1 mark. Therefore, a full 8-bit byte is represented by exactly 2 hexadecimal digits. That is just another mark. Okay, so be careful about your exams. Then multiple choice questions. Identify the main reason why computer programmers work with hexadecimal notations instead of raw binary strings. So hexadecimal is executed faster by internal CPU microcircuits. That is wrong. Okay, CPU does not work with hexadecimal, so just not that one. It consumes less space within physical RAM or storage sectors. No, it just gets the same amount of memory because it has to be stored as binary. Hex values are easier for programmers to read and memorize. Now that is the correct answer, and hex format allows more precise floating point math. Well, floating point math, no, it is just not even related to that. Okay. Then completion task, provide the corresponding hexadecimal notation symbols for the following two denary integer values. So see, it has got given as denary 8 and denary 12, and we have to just change that to hexadecimal. So 8 will be 8, that's just 8, okay? And 12, A is 10, B is 11, and C is 12. So capital C. Just remember one thing, okay? Some students lose marks here because they just use small letters here, okay? In hexadecimal, we use capital letters. Do not forget that. Explanation task, okay? So again, explain why any standard 8-bit binary integer can be represented by exactly two hexadecimal characters, and it has gotten 2 marks, okay? So you have to give 2 points. One hexadecimal digit represents 16 unique values, which is exactly equivalent to a 4-bit binary or nibble, which is 2 to the power of 4 equals to 16. Therefore, an 8-bit number can be split cleanly into two 4-bit nibbles, with each mapping directly to one hex digit. Clear? So that's it. Now, exam tips, no calculators allowed, so you have to just be very careful about the place value tables, okay? 1 2 4 8 in binary, and in hexadecimal, okay, 1 16 256, and just multiply by 16 every time. So you have to be careful about that. Build your tools first. As soon as the exam starts, write the 8-bit binary place values first: 1 2 4 8 16 32 64 128 in the margin of your paper, somewhere on the paper, okay? Use it for every conversion questions. Do not guess, so you have to just write that. And A and 10, the hex translation key. Don't try to calculate hex values in your head under pressure, okay? Because although you know them, under pressure you might make mistakes. So jot down, okay? Write very quickly. A is equal to 10, B is equal to 11, C 12, D 13, E 14, and F 15, okay? Before you answer any hex question, protect against silly mistakes. Clear? So that's about different bases. See you in the next video. Come back to learn more. Wish you all the best. Good luck and goodbye. Do not forget to subscribe us.